right? So elementary motions are the motions where either the velocity is constant or the acceleration is constant, and there is nothing special about those kinds of motions. They can be easily obtained from the basic relationships that we have seen so far, right? So just to bring it full circle for you guys, let's look at elementary motions. So what are elementary motions? Elementary motions. So the first kind of elementary motions I want to talk about are constant velocity motion. So constant velocity will say v is equal to some constant v0. So if a particle is moving, let's say, along a straight line path, okay, here's the particle p, it's moving at some velocity v0, could be given as, let's say, 5 meters per second, okay, or 10 meters per second. And it's a constant velocity, so always moving with the same velocity, right? Clearly, acceleration is going to be 0 in this case, because the acceleration is defined as a rate of change of velocity, and acceleration velocity is constant, so acceleration has to be 0, right? And it's a straight line path, so there is no change in direction either. So, but the magnitude is same, and the direction is same, acceleration is 0. So if that's the case, the relationship is very simple. We know that v is equal to dx over dt, where x is the position of the particle p from O, okay, and that is equal to v0, a constant. So in this case, it is easy to integrate this equation, right? Because I can take dt on the other side and I can integrate it, okay? So time changing from 0 to t, x changing from, let's say, initial position x0 to x. So what I'm saying is that time t equal to 0, the particle p was at position x0, and we are interested in its position at time t, okay? So x minus x0 would be equal to, since v0 is a constant, I can bring it outside of the integrand, and this becomes 0 to t, which is nothing but v0 times t. So x is equal to x0 plus v0 times t. And this is the sort of relationship that you have probably used in middle school to analyze very simple motion, where you assume constant velocity, right? So you could obtain the position of a particle if you knew the velocity, if you knew the time interval elapsed, and what its initial position was. The other kind of elementary motion is constant acceleration motion. Constant acceleration motion along a straight line path. So I'm not going to write that, but let's assume that we are still moving along a straight line path. So here is the particle p, okay, and it's moving with constant acceleration a0, which could be, let's say, a quantity called 5 meters per second squared, okay, constant acceleration. So what do we know about acceleration? Well, we know acceleration is defined as dv over dt, which is a0. So we can integrate it. So I will take t, the time variable, on the other side and integrate it. Okay. Now remember, in an equation like this, you can have only two variables. So one variable would be on one side, and all the functions associated with that variable would be on that side, and then the other variable would be on the other side of the equal to sign, and all the associated function of that variable will be on that side too. So in this case, the two variables are v and t. Okay, and this is a common mistake that students make, where they actually have more than two variables in an equation like this, and they're trying to integrate it, but they can't. So let's do that. So let's say at time t equal to 0, velocity is v0, and we are looking at the velocity at time t, right? So on the right hand side, since a0 is constant, I bring it outside and I get integral dt, which is nothing but t, and on the left hand side I get v minus v0, so I get v equal to v0 plus a0 times t, right? So let's call it equation 1. And you're probably familiar with this equation. This is one of the Galileo's equation, right? Okay, so that's just one of them. So if you know the acceleration, you know the time, you know the initial velocity, you can compute what the final velocity would be. Okay, all right. Now let's try to find what the position would be, because we know the velocity. So velocity is defined as dx over dt, where x tells you the position of this particle from the origin, okay? And we just obtained the velocity expression, which is number 1. So let's substitute that here. So v0 plus a0 times t, okay? Now I will bring dt on the other side, because this is where, on the right hand side, is where I have all the terms that involve time variable, okay? So let's integrate it, going from initial position x0 to x, time changing from 0 to 2, I have x minus x0 equal to v0 times t plus 1/2 a0 t squared. So I'll take x0 on the other side, and I get this, that I'll call equation 2. Okay, so this has three terms. You can see we have x0, we have y0t, and we have 1/2 a0t squared. So if I am looking for my final position for a particular time, and I know my initial position, I know my initial velocity, I know my constant acceleration, I can compute what the position would be. There is a third Galileo's equation which doesn't involve time actually. It involves velocity and the position and the acceleration. Now that relationship is actually fairly important, okay, for the reason I'll tell you in a minute. So let's go back to our basic fundamental relationship for acceleration, velocity, and time, which is dv over dt. Now, at this point, I'm going to actually show you something that will be incredibly useful for various problems that we'll be doing in this chapter. And it involves a technique called change of variable. Okay, so in calculus, you probably learned about how to introduce change of variable to do differentiation and integration. And that's what we're going to do over here. So our objective is really to actually get rid of the time. We don't want time in this relationship. So what can we do? We only want acceleration, velocity, and position. Okay, those are the three things we need. So this is a relationship in acceleration, velocity, and time right over here. But we want to get rid of time, and we want to introduce essentially the position instead of time. So we will have AV, but instead of t, we will have x. So how do we do that? So dv over dt can be written as dv over dx times dx over dt, right? That's the change of variable that I have introduced over here. That's great. Now, what is dx over dt? Dx over dt is nothing but velocity, right? So we can write this, and I'll bring this to the front. So I'll write this as v times dv over dx. And just by that, now I have gotten rid of the time, and I have a, I have v, and I have x over here, right? Okay, so that's great. So I have only two variables over here for constant acceleration. So I'm going to write v dv over ds. I'll bring it on the left hand side, and that's a, which is a constant acceleration. So I'll write a0. Okay, now I'll keep v dv on one side because we have the same variable, and on the right hand side I will take dx. Now I can integrate this, going from initial velocity v0 to v, initial position x0 to x. A0 is constant, so that comes out of the integrand, and this becomes x minus x0. And on the left hand side I get v squared minus v0 squared over 2, and the right hand side is a0 x minus x0. So this would be equal to v0 squared plus 2a0 x minus x0. And that is your third relationship from Galileo, right? Which involves velocity, acceleration, and position. Now remember, these three relationships have been obtained only when the acceleration is constant. And that's a very important point. So I'm going to actually write that down over here. And I'll write this actually in red, that note 1, 2, and 3 are valid only if acceleration is constant. Okay, this is very important, so keep that in mind. If acceleration is not constant, you should not try to use any of these three relationships. Okay, if you're not sure if whether acceleration is constant or not, and the problem doesn't give you whether the acceleration is constant or not, you cannot assume that acceleration is constant. Okay, so we'll do an example now. Okay, so here is an example. So let's say we have a car, and this car is moving along a straight line path. Okay, and I tell you that its initial position is over here, and this is let's say x equal to 0, and its velocity is also 0, so it's starting from rest, and then after it has traveled by a distance of, let's say, 5 meters. Okay, it has traveled by a distance of 5 meters. Its velocity is equal to 5 meters per second. Okay, now the question is, knowing initial position, knowing the final position, knowing initial velocity and final velocity, the question is, what is its acceleration? Okay, that's what I'm asking over here. So you look at the problem and say, hey, I know how to relate the two velocities when I have, position given to me as well. And I'm going to use my, this third relationship right over here, right? Which says v squared is equal to v0 squared plus 2a0 x minus x0, right? Okay. So your final velocity is 25, initial velocity is 0, 2a0, and the distance traveled x minus x0 is 5, and that gives you what? 5. 5 cancels, so a0 is equal to 2.5 meters per second squared. And you say, okay, that's my answer, right? And at this point, maybe many of you are shaking your head and saying that, hey, that's not right. There is something wrong with that. So what is wrong with this calculation? Well, what is wrong with this calculation is that I didn't tell you explicitly that the acceleration was constant, right? Did I tell you that acceleration was constant? I didn't tell you acceleration was constant. So you can't assume that. If I said that the acceleration is constant for this car when it moves from here to here, okay, then yes, this would be okay. But I didn't tell you that, which means that this is actually wrong, right? You cannot. So what would you answer? You would say insufficient information. You don't have sufficient information to actually solve this problem, right? It's not a trick question. It's just a question of paying attention to what is given to you in the problem, okay, and what you can reasonably assume. So you can assume that this car is modeled as a particle. That's a fair assumption, but assuming that acceleration is constant is not a fair assumption, okay? All right, so let's look at another example. Now I actually give you acceleration as a function of time, okay? And that is given to you as, let's say, 2t squared meters per second, okay? So I give you that, right? So now you have the acceleration. Again, if you try to use one of the Galileo's equation to solve the problem where some of the initial position may be given and the final position may be asked for after a certain time interval, you would be making a mistake. Why? Because the acceleration is clearly not constant. The acceleration is not constant. This is dependent on time. At time t equal to 0, acceleration is 0, right? At t equal to 0, at t equal to 0, acceleration is 0. At t equal to 1, acceleration is 2 meters per second square. At t equal to 2, acceleration is equal to 8 meters per second square, and so on. So acceleration is clearly not constant, which means you can't use Galileo's equation. So now the question is, if let's say you're given acceleration as a function of time, or acceleration as a function of velocity, or acceleration as a function of displacement, how would you solve that problem, right? So now we're getting into the situation where we may have to solve for these equations in a much more general way, where acceleration may be given as a function of time, or acceleration may be given as a function of velocity, or acceleration may be given as a function of displacement. In either of these three cases, we do not have constant acceleration. So we call it non-constant acceleration cases, right? So let's deal with each of these cases one by one and see, how we can, get to our requisite equation. So first one is acceleration as a function of time. Okay, so if acceleration is given as a function of time, then we know everything for the acceleration will be in terms of time variable, right? And we know that the basic definition of acceleration is dv over dt, okay? So this is acceleration as a function of time, and that means that I will take dt on this side because at is given all in function as a function of time, and I will have dv on this side, and I will have at and dt on this side, and I will integrate it, right? Going from velocity v0 to v, time changing 0 to t. Okay, in this case, at cannot come out of the integrand because at is a function of time. It has to be inside the integrand so that you can integrate it, right? So if we were to solve the previous problem where acceleration was given as 2t squared, we can solve this. So we'll write 2t squared dt 0 to t. So what is this? 2 over t cubed over 3 meters per second square, and on the left hand side I have v minus v0. So v is equal to v0 plus 2 over 3 t cubed meters per second. So this is, I made a mistake over here. This is actually not meter per second squared. It's meter per second because we're looking at the velocity over here, right? Okay. So if I know my initial velocity and I know the time at which I'm trying to compute my velocity, I can substitute for all those things and actually get my velocity. right? So in this case, acceleration was given as a function of time, and I made sure that I had only two variables in my equation, and all the like variables were on one side, and the other kinds of variables were on the other side, right? Okay. The second case is when acceleration is given to you as a function of velocity. Okay, and this happens, for things like when they are, moving through fluid medium. Okay, so when, let's say, a particle is submerged through fluid, right, and it is traveling through the fluid in the downward direction, that's the velocity for the particle, then the drag force that this particle experiences is actually proportional to the velocity. So the higher the velocity is more the drag force. And this is true for the cars and other kinds of vehicles too. Larger their velocity is larger the drag force, which is acting in the opposite direction. Okay, for moderate speed is proportional to the velocity. For higher speed, it's actually proportional to the square of the velocity. Okay, and that would be true for space shuttles and aircrafts that actually leave the atmosphere of the Earth. So if acceleration is given as a function of velocity, then what do we do? Well, we write acceleration as dv over dt, and this is a function of velocity, right? So which means the right hand side will be all composed of the terms like v square minus v cube and things like that. Then this needs to be now brought together with dv, right? So what we will have is dv over av, and dt would sit here all by itself. Okay, so integral 0 to t, velocity is changing from v0 to v, and that will allow you to compute basically how the velocity is going to change over time, right? So if, let's say, example, AV was given as CD times V, where CD is basically what is known as drag coefficient. Okay, it's a constant, and then it's given as this. Then if you substitute this in the integration, we get integral dV over CdV equal to integral dt. Okay, and most of the time this acceleration would be given as a negative CdV, because it's going to be pointing in the direction opposite to the direction of the travel, and you know that the velocity vector always points tangent to the path of the travel, right? So if we were talking about this case, v is this way, then acceleration is actually pointing opposite direction, which means it's essentially a deceleration. So this is really a negative sign over here. So we get minus 1 over cd, and this will be ln of v. So that's log base e, the natural log, v changing from v0 to v equal to time changing from 0 to t, so that's t, right? So what do we get? We'll take c dt on the other side, and we get ln v over v0 equal to minus c dt. Okay, so what is this? V over v0 is equal to e to the power minus c dt. So v is equal to v0 times e to the power minus c dt. That's the expression that you get essentially in this case. So clearly you can see that as time goes to infinity, that means a long amount of time has passed, and the velocity actually goes to 0, because e to the power minus infinity is 0. Essentially it's telling you that the particle is going to come to rest unless there was a force that was keeping it in motion for quite some time, right? So we looked at acceleration given as a function of time. We looked at acceleration given as a function of v. The third case remaining is acceleration as a function of displacement. So let's look at that. So acceleration given as a function of s, right? Okay, so what is the definition of acceleration? Let's start with that, dv over dt. Okay, now acceleration is given as a function of s. How do we integrate this? We have how many variables? We have 1, v, 2 as 2, and s as 3. So we have 3 variables over here, right? V, t, and s. We cannot integrate this. So how do we solve this problem? Well, we have to make sure that we have only 2 variables in this equation. How do we get 2 variables? Change of variable. That's what we have to do. So A is defined as dv over dt, which I will write as dv over ds times ds over dt. Okay, what's ds over dt? It's nothing but the velocity. So we get v times dv over ds. And we have done this before. Okay, now this is good because the right hand side could be a function of s now, and it's okay because we have only v and s as the variables here. So what do? We integrate v dv, and we integrate a ds. So v changing from v0 to v, s changing from s0 to s. If you know as, A as a function of s, then you can integrate this and get the velocity.